Hi, my name is JJ Lamb. I'm from the University of Wisconsin-Madison, and today I will be talking about the retest reliability of complete airway interruption methods used for aerodynamic assessment. Funding for our study was supplied by the NIH, and we have no conflicts of interest to disclose. Start with a little bit of our background here. Complete evaluation of dysphonia should include aerodynamic measurements in addition to acoustic measures. Measures such as subglottal pressure, phonation threshold pressure, mean flow rate, and laryngeal resistance are 4 metrics that are of interest. Performing aerodynamic assessments has shown promise in being useful alongside acoustic and endoscopic methods for diagnosis. In our study, we compared 2 methods of measuring aerodynamic parameters. The first method is the labial method. This method is the operating principle behind devices such as the Rothenberg mask or the K-Pentax PAS machine. However, it has been believed that the labial methods are at risk of instability and can be hard to perform with untrained subjects. Our lab has done a series of studies using mechanical methods of airway interruption to determine if those methods offer any additional reliability. In the present study I'm going to talk about today, we focus on comparing the retest reliability of these 2 methods. In our study, we directly compared the labial and mechanical testing methods. A schematic of the experimental setup is shown here on the right. For both tests, the subject phonates into the proximal end of a PVC tube. So right here is the proximal end. And then within the tube, we have ports for measuring pressure, airflow, and a microphone for recording sound and audio. With the labial method, an anesthesia mask is attached to the proximal end of the tube, and an intraoral tube was extended into the subject's mouth to measure pressure. The subject has to say "pa" 5 times per trial. To measure subglottal pressure, the subject was instructed to phonate at a comfortable volume, and to measure phonation threshold pressure, they were asked to phonate as quietly as they can but without whispering. When we switch over to the mechanical methods, the anesthesia mask is replaced with a silicone mouthpiece. This looks kind of like a mouth guard. The subject used a set of nose plugs to block their nose, and then phonated a constant "ah" for a 10-second trial. During the trial, a balloon valve at the distal end, so over here, this is the balloon valve, was inflated 5 times for 250 milliseconds to interrupt the subject's phonation. During each interruption, subglottal pressure and phonation threshold pressure were measured. For our testing, we had 55 subjects over the age of 18. Subjects performed 10 trials with each the labial and mechanical methods. In order to test the retest reliability of these methods, 30 of the 55 subjects came back for a second session 2 weeks after the first session. The second session was exactly the same as the first. To determine the retest reliability of each method, we calculated the percent difference in coefficients of variation for each metric measured at both sessions. The image shown here is an example of aerodynamic data collected with the labial method. The pressure trace is shown in blue and audio is in red. When the subject says "pa," the pressure increases as measured through the intraoral tube right before the subject's lips separate. The maximum pressure occurs right before the audio begins. That's up here. And then when the subject is phonating at a comfortable volume, this maximum pressure represents the subglottal pressure. When the subject is phonating quietly, the maximum pressure represents the phonation threshold pressure. During labial trials, the mean flow rate is calculated by measuring the subject's airflow during the phonation phase of the task. To calculate laryngeal resistance, the average pressure measured across the entire trial is divided across the mean flow rate of the entire trial. Resistance is calculated in this way to keep analysis consistent with how it is calculated for the mechanical trials. This image shows the data collected from a mechanical interruption. Pressure again is in the blue and the audio is in red. Because the subject is saying "ah," phonation is constant until the balloon valve inflates and initiates the interruption. While the balloon is deflated, the pressure in the device is at 0. At T1, down here, the balloon inflates and blocks the tube, causing the pressure in the tube to start to increase. We are measuring supraglottal pressure within the tube, and during each interruption, this pressure will equilibrate with the subglottal pressure. At T2, the audio goes down to 0 up here, and the pressure is marked at that time. T4 is where the subglottal pressure is marked. This is set at 150 milliseconds after the interruption based on previous research done at our lab for a reliable time constant for subglottal pressure. To calculate the phonation threshold pressure, the pressure marked at T2 is subtracted from the pressure marked at T4. In other words, phonation threshold pressure is equal to subglottal pressure minus the pressure measured at the phonation cutoff. To measure airflow during these trials, mean flow rate is taken during the intervals between balloon interruptions. Because there is not a dedicated portion of airflow that directly corresponds to each interruption, laryngeal resistance is calculated as the mean of the subglottal pressure for the trial divided by the mean flow rate of the entire trial. We'll start our results with our pressure measurements. For our retest metrics, we found a significant difference in the coefficient of variation, or COV, and percent difference for the subglottal pressure measures. In both cases, the mechanical methods had lower variability. You can see that depicted here in the box plot on top, first coefficient of variation, and then lower for percent difference. Something surprising that we found in our study was that these two metrics were actually very similar for phonation threshold pressure. We had hypothesized that the mechanical methods would have better reliability measures for PTP. However, we see that both the COV and the percent difference metrics were similar for both. The data in the table is the actual pressure measurements in the units of centimeters of water. I would like to point out that the mean PTP values, which were significantly different between mechanical and labial methods. So here we have the mechanical PTP and the labial PTP. We believe that this difference is explained due to the hysteresis effect of the vocal folds. The labial method measures phonation onset, whereas mechanical methods measure phonation offset. Given this, it makes sense that we would find that mechanical PTP is significantly lower than labial PTP. Moving on to airflow and resistance measures, we found that mechanical interruption had lower COVs and percent differences than labial methods for both measures. Looking at the graphs, we see a much wider distribution of values for labial than we do for mechanical. We also determined that there were significant differences in the mean values of airflow and laryngeal resistance, with mean flow rate being higher for mechanical and resistance being lower for mechanical. This ties back into what we see with the reliability data. When performing data collection, we made many observations about how some of the subjects struggled to get the anesthesia mask used with the labial method to create a complete airtight seal around their face, which would lead to pressure and airflow leakage. These issues were not seen with the mouthpiece used for mechanical methods, and that is reflected in the reliability of our data. When we began this project, we expected to show that the mechanical methods would be more reliable for measuring phonation threshold pressure than the labial methods. However, of our 4 metrics of interest, PTP was the only one to not show any differences between methods. Subglottal pressure, mean flow rate, and laryngeal resistance all showed superior measurement reliability when using mechanical interruption. Due to this, further research is warranted into the diagnostic capabilities of these metrics. When we were working on publishing this research, one of our peer reviewers commented that our methods were measuring onset and offset phonation. They pointed out that the hysteresis may affect the intrinsic variability of these measurement methods. I thought that this was an excellent point and that the hysteresis phenomenon is something that we would like to look into the future. Could this intrinsic difference offer any better diagnostic tools? Based on our data here, it appears that measuring conditions of phonation offset results in better reliability of measurements, so this does have promising diagnostic capabilities. And with that, I'd like to thank the Voice Foundation for allowing me to give this presentation today, and hopefully you were able to take something away from it.